Okay, I know we in class we got to different locations and different periods, but I'm going to go ahead and give you some examples of how to do the orbital notation with the shortcut, and then show you a couple quick examples of electron configurations. Let's take and do the orbital notation for Cobalt. If we do that, we're going to have CO, and if we do it the long way, we're going to have 1s, 2 arrows, 2s, 2 arrows. And we're just following the periodic table in order as we go along. And you see each time as we hit a new area of the table, just adding to it. Now we're in the third energy level, P, which is going to be argon. After that third energy level, we're going to 4s, because that's the next part we encounter. And now we're going to enter into the D block. Now in class I mentioned it, and we'll reinforce it again. The energy level for those atoms in the D sublevel are going to be 1 less than the period number. Since Cobalt is in the 4th period, we are going to have its energy be 3D. And the D has 5 orbitals. Cobalt's going to have a total of 7 electrons. So we have 1, 2, 3, 4, 5, 6, 7. So that would be Cobalt. Now that process is kind of long, so we actually do have a shorter way of representing this. And the shortcut involves taking these, and since they are exactly the same thing as the noble gas argon, we would simply write Cobalt, and we put AR in brackets. Now that AR in brackets is representing all of those electrons, so we don't have to rewrite them. We then pick up where argon leaves off, which after argon is 4s, one line to represent the one orbital with the 2 arrows, and then again 3D, because the energy level for the D sublevel is 1 less. We have our 5 orbitals, and we got 1, 2, 3, 4, 5, 6, 7. So we have the ending part, starting with the 4s, being the same in both of them, because those are the electrons represented after the noble gas. Let's do one more. We will do, in this case, antimony. So antimony is element number 51. Its symbol is SB. The previous noble gas, and we can only do the shortcut with the noble gases, which are those elements in group 18, is krypton. So we put Kr in brackets. Now the Kr is going to represent all of the electrons that occur from the first energy level all the way up through krypton, which is in the 4th energy level P. We then pick up where it leaves off, and it's going to leave off. The next part's going to be 5s. S has only 1 orbital. It can hold 2 electrons. After 5s comes 4d. Again, the D block is going to have an energy 1 less than what the period number is. And since we're in the 5th period, the energy for the D is going to be 4. We're going completely through the D block, so all of them will be filled with a total of 10 electrons. And after 4D comes 5P. And we're going to have, with that 5P, 3 lines to represent the 3 orbitals that are in the P sublevel. And antimony is 3N. So we would have 1, 2, 3, arrows to represent antimony. Now, electron configurations are an even more condensed version of this. In electron configurations, we don't worry about the orbitals and the spins. So let's do nitrogen. Nitrogen's electron configuration, the process is going to be very similar. We start off again in the first energy level. We are in the S sublevel. But instead of drawing a line to represent the orbital and the two arrows, we're going to put a 2 to represent the total number of electrons in the S sublevel. We would then put 2s, because that's the next section we get to on our way to nitrogen, and we put a 2 because it's going to have 2 electrons in there. We then do 2p, and we see that nitrogen is the third over in the p block, so we would put a 3. And if we add those exponents up, we will get a total of 7 electrons, which is how many electrons nitrogen should have. Let's see a slightly longer one. Let's go ahead and do iodine. No, we'll do astatine. A nice long one. So astatine is AT. We start off in the beginning. 1s2, 2s2. And again, I'm following the periodic table. I'm just not taking the time to count up the number of orbitals that are going to have to be there. 2p6, because there's 6 columns in the P. After 2p6 comes 3s, 2 electrons, 3p, 6 electrons. Next in line comes 4s, 2 electrons. Then we do 3d, again because the d is 1 less than the period number. So 3d, 10. And then 4p is next area on the periodic table, 6. 5s, 2. Next area is going to be the D block. We're going to go to 4d because it's 1 less than the period number, and we're in the 5th period. 10. 5p, 6. Next up is 6s2. And then we're going to drop down, and if you look very closely at the periodic table, after barium, number 56, we go through the F block. So we're going to have 4F14. Now the reason why it's 4F is because just like the D, the F is going to be 2 less than what the period number is. So those elements, cerium through lutetium, those are all part of the 6th period. The F block is, the energy is 2 less than the period number, so it's going to be 4F, and there are 14 in the F sublevel. We then go back to the 5D, and then we're going to have 10. It's 5 because it's 1 less than the period number, and then we have 6P, and it is the 5th one over in the P sublevel, so 6P5. Now obviously that's way too long. I would never have done that for orbital notation, but let's apply the shortcut. If we look at the periodic table, we will see that the previous noble gas on the periodic table before astatine is xenon, and xenon ends with 5p6. So all of this is represented by xenon. So for astatine, we would put AT. We put XE in brackets to represent all of those, and we simply pick up where we've left off. In this case, 6S2, 4F14, 5D10, 6P5. And do one more and show it with the shortcut. Let's do a little bit of shorter one this time. Let's do germanium, so GE. The previous noble gas for germanium is going to be argon, put in brackets. and we pick up where it leaves off, and that's going to be 4s2, 3d10, 4p, and germanium is 2n,